Perfect. Thank you. All right. So hi, everyone. My name is Alyssa Adams, and I'm a postdoc trainee at the University of Wisconsin-Madison. I'm in the Anand Tharaman lab in the Department of Bacteriology, and I currently look at how viruses interact with their hosts. So, but this project that I'm going to be presenting on today is a side project that I've been working on, and I've been trying to understand how to understand emergence and how we can quantify it a little bit mathematically in physical systems. So I also have a picture of a plug as a sort of a nod to the Gestaltist idea of emergence, where it's the whole is different than the sum of the parts. So there's this idea that you would see faces in things and shapes. So that's just a small little nod to that. So just a little bit of context in the things that I study. So my long-term research goals are to really understand the intersection of the theory of computation, physics, information theory, and biological evolution. So I like to ask questions such as how much energy does it cost to run a computer program in real biological systems? So other questions that I like to think about is, so there's a picture of this pole over here, a telephone pole. I know it's a high traffic information area because of all the staples. So information in this case makes this telephone pole look different than all the other telephone poles because it's physically has different characteristics because of sharing information. So what I really want to know is, how are living systems different than non-living systems in terms of mathematical frameworks that we can put together and mathematical models. I'm also really curious about understanding how life arranges itself in physical space to perform computation. So thinking about things in terms of proteins, it's something that's a sort of mantra in biology is that structure equals function, especially for proteins. So I'm really curious about understanding that. And also I'm trying to understand how what biological data can tell us about emergence. So, what are the mechanisms behind emergence? Because we have so much data out there on, bioinformatics between viruses, bacteria, and also human social systems and other sorts of data on the internet. So, okay, so that's a little bit of an overview. So I wanted to share 3 ideas that really sparked this project idea. So the first one is, are biological states discovered or created? And this is something that is from the Reconceptualizing the Origin of Life workshop in 2015. And what this is talking about is, as biology is evolving and going through different states, is biology bootstrapping itself in terms of opening up possibilities from its current state, or is it simply filling in states that are already possible? So I thought that was a really interesting discussion. And then another point that I wanted to address was from this paper from 2017 that I really like. Is talking about open-endedness, especially in the perspective of artificial intelligence. So they were talking about how novelty search in AI and machine learning really only addresses finding new solutions to existing problems open-endedly, but they don't inherently generate new kinds of challenges to be solved. So the most powerful open-ended system would generate both. So, there's different kinds of ways that we understand open-ended evolution and open-ended systems. But what they're arguing is that a really strong open-ended system like biological evolution that in the Earth's history is not just solving problems, but also creating new problems for it to solve. And then finally, the third point was from the last open-ended evolution workshop, which was 2 A-Lifes ago, I believe. David Ackley made a really interesting point that A-Life models are stuck in a box. So, they're not going to be accessing brand new state spaces. In other words, they're not going to be introducing new problems for it to solve because they're in a box and they're not receiving information from the outside. So I was really inspired by these 3 points to really dig deeper and try to understand what's the relationship between a system's available states and what state spaces it's operating in, and also emergent phenomena and how that's related to open-ended evolution. So I really thought that from thinking about these three things, that emergence is probably really necessary for understanding how open-ended evolution is working, and I think they're very related in some sort of ways. So let's dive right into what I mean by emergence and all the different things that people are thinking about what emergence is. So one of the most famous quotes that's often misquoted is the whole is different than the sum of the parts. It's usually misquoted as the whole is more than the sum of its parts, but it's the whole is different than the sum of its parts. So, this is cue the video of starlings, the flock of birds that usually flies around is usually an example of what people talk about when they say emergence. But I really love this paper from 1997 from Mark Bedeau talking about weak emergence. So there's two types of emergence that is addressed in this paper, which is weak emergence and strong emergence. So weak emergence is usually when we colloquially talk about emergence, like the cat emerged from under the bed, Ebola emerged once again. That sort of falls under weak emergence, but also this idea that if you have a state space, you're expanding a state space. So you take a set of possible states. So like if we were looking at words as a state space, we could think of all the different sounds and letter combinations to come up with all the possible words that you could say within a given language. And weak emergence says that you go from a possible state to an instantiated state. So if we're thinking of word state space as an example, and a recent example is this word chuggy that has recently emerged. It's a Gen Z word for lame, pumpkin spice lattes and Ugg boots and Minions memes and stuff like that. So, like 20 years ago, that word was certainly possible, right? But recently it became something that was a possible word to an actually used word on the internet. So that's an example of weak emergence. So strong emergence, on the other hand, is more strong, obviously. So it's a more deeper concept of emergence. So like the emergence of multicellularity or the emergence of language. So in terms of states and state spaces, what this is saying is that strong emergence is addressing the appearance of an entirely new state space. So going back to the word state space example, hashtags was a set, or it was a state in the possible word space if you're considering symbols as being part of like your words that's typed, but also it's a set of states. So what it's doing is you're saying, okay, we're going to take this state or a set of states and we're going to expand upon it, and now we're going to be using this hashtag state space, which came out of the word state space. So it's a little bit different than it's not just expanding your state space, but it's creating an entirely new state space for our system to operate in. So I also highly recommend reading this book. It's super good. It's got all kinds of really great ideas on emergence, and it's so fun to read. So, my question was, okay, so how is the system discovering new states? And, but more importantly, how is the system discovering new state spaces? So to be precise, once again, or a little bit more precise, a state is a possible configuration of a system given some sort of set of variables. So if you're thinking of like a Cartesian coordinate system, a state is simply a configuration of your x, y, and z variables. And your state space is, you can think of it as the topology of which all your possible state spaces lays and how they're all relating to each other. So that's your whole entire Cartesian space. So we felt a little bit more confident. So like in my PhD work, what we did was we explored this idea of open-ended evolution in discrete finite cellular automata systems. And we felt much like a lot of like really confident in terms of understanding how open-endedness is related to a system exploring different possible states and how to get there. So what we found in these sorts of systems was that a open-ended evolution is telling a system how it moves within a single state space. So what we have is in this figure over here, we've got a system that can be in 6 possible different states. And according to the dynamics, the system can be going from one state to another state depending on the dynamics. So in this case, since it's cellular automata, the dynamics are cellular automata rules. So in this example, in A, you have, if you started in state 3, then you can only go from 3 to 5, 3 to 5, according to these dynamics under dynamics of alpha. But if I switched up the dynamics, and even if I had the same state space, what I get is a completely different state space topology. So if I started in state 3 again, I would only stay in state 3 forever. But if I were to change my the different dynamics as I go along, so if I'm able to choose from alpha and beta dynamics, I can come up with an entirely new trajectory on my state space. And of course, if I really wanted to dig deep into the technical details of different ways of understanding open-ended evolution, I could get a really, really long trajectory that isn't repeating itself, depending on how I'm merging different ways to access different dynamics together in one. So, in other words, what from this work, what we learned was that for bounded discrete deterministic systems like cellular automata, open-ended evolution is only possible in an ensemble of subsystems because you have to have something external to be telling the system in how to change its dynamics over time. But what this is again, what this is telling us is not how to come up with an entirely new state space, but how to traverse a single state space. So that's how we're understanding open-ended evolution. But it's like I said, it's not necessarily addressing this idea of coming up with an entirely new state space. So so I felt pretty confident about this first point of how is a subsystem discovering new states. That's weak emergence, and that's something that we explored with this idea of open-ended evolution in these kinds of systems. But also we wanted to, but now what I'm really curious about is how is a subsystem discovering new state spaces? So, okay, so how does it happen in cellular automata? I'm not really sure, but if I could think of a real life example in terms of Twitter, I know that they expanded and are using the hashtag state space, which is, pound followed by some sort of letters, in order for users to perform some particular computations like sorting and searching on tweets. So it tells me that in real life examples, state spaces are selected upon in order to perform some particular computation. So, as a sort of like a side note, I was thinking a little bit about okay, state spaces, right? So if I have a system, what are all the possible different state spaces that I could describe my system in? So I saw this really cool show on Netflix talking about the art of design and all the different things that go along with it. And in the beginning, in the part of the show, they had this episode on emergence and how the state of an observer is affecting how an observer can interact with their environment, which I thought was really cool. So they had like an example of like a sodium lamp. So a room was lit up by the sodium lamp, which makes everything look monochromatic. And the art piece was exploring, how does that a observer's perception affect that? So another example that they talked about is a rainbow. So a rainbow is created because EM waves are being refracted through water vapor at a particular angle with respect to the observer. But the appearance of a rainbow is completely dependent on not just the light going through the water vapor, but it's also totally dependent on the angle at which the observer is looking at the cloud vapor. So from particular angles, you're not going to be able to see a rainbow. So they talked about how a rainbow is an emergent phenomenon, but it totally depends on how the observer is interacting with it. So I thought that was really cool. And I sort of like ferreted that away in my mind as, okay, so detectability of emergent phenomenon is going to depend on the state of an observer. So if I had some sort of system, regardless of what my system is and what it looks like, I'm able to describe that system in tons of different state spaces. But as an observer, I'm only going to be able to access a particular number of those state spaces because of my own physical state. So, for example, like if I wanted to say, oh, I want to access more state spaces, what I would need is I would need additional physical modifications in order to do so. So, one of the things that humans are really good at is coming up with these sort of tools so we can access new state spaces. For example, like telescopes, even though those dynamics are happening out there in space, looking at these distant stars and celestial bodies, we're not able to access them until we have tools and for us to be able to observe those particular phenomena. So, okay, so that's fun about systems and things like that. But so I thought, okay, so if I'm an observer and I'm observing some sort of system and I have all my different state spaces, I can sort of order my state spaces according to like their coarse grain level. So on one hand, I can have like a really high leveled order of description. So an example is like a two-state system of, is the system in existence or not, yes or no. So like a binary high level coarse graining. Or on the other end of the spectrum, I can have a lower level state space. So things that are very fine grained, right? But what I'm really curious about is, okay, given all of my different state spaces, all my levels of description for a system, how is that topology looking like for each of these different states? So in other words, what is the topology of how one state evolves into another state as the system is changing over time? And how is that topology of different state spaces relating to each other? And if I can get a handle on this, is this a good way to try to understand or predict emergent phenomenon? So emergent phenomenon is something where you can think of a dynamics in a particular state space that weren't necessarily accessible to an observer before. So what does that look like in terms of topologies here? And so I'm really curious to know specifically, how is emergence and state spaces, and state space topology related? So in order to answer these questions, I did a little bit of applied philosophy. So I took a toy system of an Ising model. And an Ising model is really famous for its phase transitions, which I would argue is something that's like an emergent phenomenon. I'm going to take a peek at the chat. Okay. So, and just to make sure there's no questions, because it's totally fine if you have questions, you can put them in chat and I'll see them. So, so the up and down, so this is how a Ising model works. So you have like a grid of cells, right? And each one of your cell can be in one of two states, which is like an up state or a down state. And what happens is these different cells can flip depending on the temperature and depending on the states of the neighbors. So the goal of the Ising model is for it to flip all of its up and downs to find the lowest energy, which creates really interesting behavior as you change the temperature of it. So there's a critical temperature in an Ising model, which basically says that at this critical temperature, all of your cells are going to either be pointing up or they're all going to be pointing down. So it's a fun, interesting phenomena. And what I wanted to know is within the simple toy model, I wanted to look under the hood, and I want to do like this whole like understanding all these different state spaces and how their topologies are really like relating to each other. So, and I also want to know, are some state spaces more deterministic than others? And it's kind of a weird question, but the reason why I wanted to answer it is to think about like what a deterministic state space looks like is because I'm really interested in predicting emergent phenomenon, right? So if I have a complex system of like all these different state spaces with all these different levels of description, one question that I'd be interested in asking is, given the current state of a lower level description of a system, which is often what we have access to when we're looking at data on the internet, for example, I want to know not just what the future state of this state space is at some future time, but I also want to know what that future state is in terms of the coarse grains level. So not just looking at the future of a particular, like what the system is going to be in a state at a particular state space, but on multiple different state spaces, which I think is one of the more interesting, well, one of the most interesting questions, open like problems to solve in emergence. So in terms of like the different state spaces that I'm looking at, I'm only going to be looking at the spatial state spaces. So I took this 9x9 system and I broke it down into all the different possible spatial state spaces. So, like the whole 9x9, individual cells, adjacent cells, cells that don't go together. And I'm going to run it 1,000 times and check out and just say, okay, what's happening in all these different state spaces? Is it interesting? So going back to this idea of what a deterministic state space is. So say this is my current state space. So these two adjacent cells, and the current state of this state space is down up. So that's this node right here. And a totally deterministic state space would look like this. So given I'm currently in a state, I only have one option of another state that I'm going to, because if my state space topology looks like this, that means it's something that I can use to predict the dynamics in the future. Because on the other hand, if my state space looks something like this, it would be really hard to predict what's going on in the future. Because if I'm sitting in this current state, that means I could go to this state or this state or that state, and that's really difficult to make predictions about things in the future. So the way that I estimated the deterministic fraction of a state space was just a very silly, simple, like counting fraction. So given my state space topology, and after looking at the dynamics of how one state goes into another state for that particular state space, I simply counted the nodes or the states with exactly 1 out degree, and I divided it by the total number of states or nodes that's in my state space. So after I did that, what I sorted all of my results by the size of the state space. So on the x-axis, I have state spaces that are 1 cell large. So that's like that little corner in my Ising model. And my deterministic fraction for that example is 1. So that makes sense because in this, for 1 cell large, I only have 2 states. And if I'm in the up state, I can only go to the down state because I'm not counting self loops. So the deterministic fraction is 1 because my state space looks like 2 nodes, and it has 1 arrow going from one state to another state. And it's a little loop like that. And then for 2, sorry. So for 2 cells, I have 4 possible states, and it literally looks like that is my state space. And this state space has no nodes that have exactly 1 out degree. All nodes have exactly 3 out degrees. So my deterministic fraction is 0. But as you can see, as I'm increasing my state space size, I'm getting more and more determinism as things go on. But I thought, like, okay, so why is this happening? And it turns out that it's because larger state spaces have less time to explore different states. So because each state space is exploring different states for the same amount of time, state spaces that are much larger have a lot less likely it's a lot less likely for the system to reach the same state more than once. So it's only apparent determinism. So I thought that was something that was really interesting because if I was thinking about human systems that are doing the same thing, I'm wondering, like, okay, is that like also apparent determinism there? So, but I think the most interesting result from this analysis was if I just took like all my state spaces, regardless of their size, and I lined them up in a ranked order according to their deterministic fraction, and each one of these lines is the simulation at a different temperature, and this is all over 1,000 different runs, and you can see the error bars are the shaded regions, and what you get is you get this interesting curve of variety of curves. And I have this one highlighted here because this is the closest one to the critical temperature. And this is one that's looking linear, which I thought was really interesting. So what it's telling me is as you have your hotter state spaces down here with the higher temperature, you have a lot less determinism because things are flipping around a lot more because it's hotter. But if you have something that's a colder system, your bits aren't flipping as much, and you get something that's a lot more deterministic because things are colder and things are are slower. So I thought that made sense, but I thought this was actually a nice way to view the phase transition in a slightly different way. So like this is the phase transition, the critical temperature is solvable analytically, but I thought this was another nice way to be able to see that. So this is also a blend of the last two plots. So each point is a result of the simulation. And so this is just saying, okay, just give me like, forget what size your state space is. I just want to see like, how is the deterministic fraction related to the total number of bits that are flipped? And so this bits, the total number of bits that are flipped is also normalized according to the state space size. So like 100% of the total bit yeah. Oh wait, no, it's not. Anyway, so but basically what this is saying is as your deterministic fraction is getting larger, you're actually flipping more bits. So I thought this was a pretty surprising result, because it's saying that the more deterministic your state space is, the more likely you are to be able to flip a lot more bits. So there's a lot more activity going on, which I didn't expect. So in conclusion, like I said, in general, for this example, for this toy system, more bits are flipped in state spaces that are more deterministic. And I also want to know what's going on around the critical temperature in regards to determinism of all the state spaces. So that's that curve, that's that plot of all those different curves. I also want to look at larger models, because this was just a tiny 3x3 grid. But I also want to know how are these results changing with an external magnetic field? So I don't have a magnetic field in this example, but it would be really cool to see how these results are changing with additional forces. And of course, I want to know how is this work building towards a general mathematical framework that can mechanistically explain and predict emergence in the future. So thank you very much. I am very excited to hear any questions, comments, criticisms, anything. This is a really fun project that I love working on, so I'm happy to hear any thoughts that you might have. Thanks.
Thanks, Alyssa. Great talk. I think there's one question in the chat that I can see. Lana says, is that just because there are bigger states need more time? I think that's the...
Yeah, so I think this is in regard to, this here, I think maybe. I hope. But yeah, so like the states, right, exactly. So that's exactly what's going on here is like, because if a state space is bigger and you have the system that it's only exploring a finite number of states, yeah, absolutely. So you have apparent determinism simply because like the system hasn't had a long enough time to explore. So like this is kind of related to this idea of like open-ended evolution. You know, a question that I get sometimes is, you know, if we ran biology 1,000 different times, would it look different each time? I think it's a little bit related, because we don't actually have the time to run biology 1,000 different times and see what it looks like. So we have, so it could be completely like predictable, or it could be completely random, but we're not sure because we don't have a long enough time to explore the system.
Yeah, I think maybe we can have two more questions. Maybe Dragonet says, have you considered stochastic state space at lower levels?
Considered stochastic state spaces?
Yes.
Oh, at lower levels. Let's see. Yeah, I guess that's kind of what I was trying to get at with this deterministic, like this deterministic fraction. I hadn't like necessarily honed really into the idea of like how stochastic something is, but that's what I was trying to capture with this idea of deterministic fraction. But I don't know if I really like did, you know, I don't know if it was like the best way to go about it, but yeah. So I was considering like, because like if you have I guess like a state space that is much smaller, it's going to appear a lot more stochastic because it's had a lot more time to go over all these different states. And because it's an Ising model where it's like kind of like each transition is dependent somewhat on randomness, you are going to get a lot more stochasticity in those levels.
Very quick one. Hiroki says, when you count states, did you consider symmetry? For example, rotational symmetry in space?
No, I didn't, and I definitely should because I think that's a really great point, and that's something that I really want to look at as well.
Great, thank you. Sorry about cutting into your time a little bit there, my mistake.
No worries.